the same sets given. Because of the universal set, we drew our Venn diagram, and this is what we got as the outcome of our A intersection B complement, which we just got from the simplification of what we had by introducing the complement on each set. So we just introduce the complement everywhere. You're okay with this, right? Yes. So now the rest should have been done in a similar way. Yeah, just using a Venn diagram, it just shows clearly what region you're interested in. Then now, using the algebraic set laws, they're asking us to simplify each of the following, and they did not specify how the sets are related. The only thing we have to do is to work with what we have until we have reached at a stage where we cannot simplify it any longer. So like the first one, we have what? We have our P. They're saying P complement union. This is what? Union Q minus R. Then this whole thing is given to be having a complement outside this first question there. Yeah, so we don't know how P and Q are related, and R, we just say this is going to be this because of the minus. You're okay with the minus changing, right? Then we can introduce the complement throughout. This is going to be P, complement of a complement, so this cancels. Then the sign here, the operation changes from union to intersection. Then we have Q complement union R. So this is what we have. We just leave it here because there's nothing that is common. It's P, Q, R. We cannot even relate because the only thing we can relate them is by us expanding them, which will be something longer than what we have. So this is a simplified form of this question. Is this okay? Yeah, so the next one here is straightforward. They're saying X union. This is X union. There is Y intersection X. So are you okay if I say the answer here is X? Because whatsoever is common between Y and X is a subset of X, because union means addition of what was common between X and Y and the whole set X. So the best case scenario you can be assuming whenever they do not specify the relation of the sets is you assuming that there's an intersection between the two. So we're taking this case. Yeah, so when they say X union, X intersection Y, we're just saying X union. We can just plug in the numbers. So the numbers we can use here is X is 2, 3. That's a set, 2, 3. Then union, the intersection of X and Y is a 3. You notice that the union brings us back to 2, 3, which is just the same as X, right? Your part 2 of question number 2. So the same, even this is just something that was already expanded. We just have to compress it. We're able to see something common. It was the distributive law of sets. Whenever you have two sets, we can always distribute. Let's say I have these two sets, I mean like here, with two different operations. So this can be distributed as A intersection B, then bring the union on the middle, then you have A intersection C. Or if it was A union, then the guys here, they're having an intersection, that would be A union B, then intersection A union C. These are okay, right? These rules are okay. So what they gave us here is something we can spot to be M intersection N union N complement. Is this okay? Because what is common here is M and N, M and the complement, I mean the intersection. Also we have M and the intersection. So imagine we remove this and we remove this. What remains is just N union N complement. You see that, right? Yeah, we remove the M intersection, remove this guy and remove this guy. We'll have N union n complement. That's going to give us any set union its own complement is a universal set, right? Yeah, the rules are that if you have any so okay, so you're asking about this one only. Say any set union its own complement to give us a universal set. So it's like, imagine you have a set like this, then there is A here. This is our A. There's 1 and 2. Things outside A is 1. Things inside A is 2. So addition of everything outside A and everything inside A will give us the whole universal set. Oh, yes. Yes. So inclusive of the other sets as well, yes. Yeah, so the answer here is going to be, and then we say any set intersecting the universal set is going to be that set, because that set is a member of the universal set. So what is common between everything and something that's found in everything? It's that something, that's the only common thing. So that's how the answer here becomes to be M. Then this here, when they say A minus B, this guy here, it's just, you know how A minus, we're saying A minus B, so we can change this to A intersection. You have A intersection B complement with another complement. Is this part okay? This part here, they're saying it's okay, right? We have A intersection B complement and that, so we're just going to say A intersection A complement union B there. Union A intersection B. Is this part here okay? Yeah, so this is how we do this guy here. Then this one here, when we try to simplify it, that's going to be the same. Just change the minus, it becomes A intersection B complement, then introduce the whole complement which is outside. So this is going to be A intersection B, then intersection, you have A, then intersection this guy, because you have what? You have A intersection B, there's a complement outside, union, there's A minus B, then there's a complement outside. So this is going to be A minus B complement, there's a complement outside, introduce the complement everywhere, that will be A intersection B, then intersect A complement union B. Yeah, so are you okay up to this stage here? Then it's okay? Then from here, we're going to distribute. There's A intersection B, A intersection B, intersection A complement. Then we bring this union here. Then again, we go A intersection B this side. Then from here, so this came here on the middle. Yeah, so this is going to be A intersection A complement. The operation is the same throughout, so we can just rearrange them to bring similar or rather like terms near each other for them to deal with each other. So A intersection A complement is an empty set intersecting B. This is union A intersection B. Then this is going to give us what? An empty set union A intersection B. This will just give us A intersection B. Okay, so you're okay on how we moved from here to here, right? We just this intersection. Okay, so we had A intersection B, then this is intersecting A complement union B. Yeah, so we're saying we have this intersect with A complement. That's where this came in. This part is okay, right? Then bring this union here in the middle. That's a union. Yes, it is, yes. Yeah, so we're treating this to be like one set. It's like how the thing I said to say you can distribute the distributive laws. Yeah, so we're treating the whole A intersection B like what I gave you was just for one set. Like this, you could have said this is that. So now we're treating this whole thing, this as one set. Yeah, no wonder we're able to do this. Again, we say this intersection, the last thing there. Yeah, so that's what we do. Yeah, then from here now, since it's intersection, we can rearrange to bring the letters that are like close to each other so that we see how they're relating. And in this case, we are having what? We're having A and A complement. That's where the A and A complement came close. It's two intersection, so nothing really has changed. We just rearrange. Then here, we already have this. This part is a B. That's how the B came about. Then here, this gives us an empty set. Yeah, so this is why everything we did happen. Then here we have what? We have an empty set union A intersection B. Then this just gives us an A intersection B. Yeah, so you can try the last one, then you send for me. Yeah, this last guy here. So this here, there's B. So just distribute the B complement throughout, then you see what you'll be able to simplify. Then as soon as you notice you cannot go any further, meaning that's the furthest you can go, that's the simplified version. Yeah, so for this case, question 2, they did not specify the relation between the sets, but for number 3 they specify. They say the sets are disjoint, meaning they have nothing in common. Disjoint sets just mean that if you sketch your A and your B, they have no intersection. They look like this in a Venn diagram. That's what we're using for these guys. Yeah, so I'll just solve the last one. It will be able to help you to understand everything. They're saying A union B minus B, A union B, then minus B. That's what they're saying. Yeah, this guy here. Yeah, so if they are disjoint, it's easy because you can just use a Venn diagram to illustrate, to see, to visualize what is happening. So this is A union B, then intersection B complement. That's what the minus does, right? So A intersection A union B is just 2 and 3. You can get that from here, 2 and 3. What is in A plus what is in B? Then intersect with B complement. What is outside B? That's simply 1 and 2. Then what is common between these two sets is just 2. So the answer is just supposed to be A. Set A, right? This guy here, if you sketch it, that's our answer. So we're using the Venn diagram. You can use the Venn diagram always. Just take into consideration the fact that they say these are disjoint sets. Yeah, so this is okay, right? Then these are intervals. I'll just give you a summary of the intervals. So we have notations when it comes to intervals. When it's an open interval, we show using these brackets, meaning it's open. We show it like this. We say, let's say there's A and B. it's open, we show it like that. You know, to say if it's closed on both ends, we'll just show A and B. You know how we just close it here, we close it this side. It can be half open, half closed. Yeah, so you know this already. You have, let's say, A open, then let's say B is closed. Yeah, then the other one you can have what? You can have closed then open. Yeah, so it's the same thing, just vice versa again. So we can show them on the what? On the number line. Write each of the following, or here, 4, they want us to show on the number line. Then infinity and negative infinity are numbers that we show this side. Okay, so how we can talk about infinity, negative and positive infinity. Yeah, so we're saying whenever they talk about infinity, these are like the end values, this side and this side, that we can always be imputing whenever we need to just restrict like the whole set of number line, really. So if they say 0 less than, like this guy here, they're saying on the number line, and they're always going to be open. Negative infinity and positive infinity, they're always open. So like this one, we just show from 0 closed, then going to negative infinity. Yeah, so number 4 is okay, right? Okay, so the same applies to number 5, except we show this in an, let's say, in set builder notation. Set builder notation is a notation like this one here. Yeah, this one, that's set builder notation. So like the first one, it will be x is such that it's a real number which is closed between -1. It's closed at 1, so we say less than or equal to x, then less than or equal to 1. This one again, it will be x is such that it's a real number, -4, but it's open at -4 and closed at 1. This one is open both sides, so it will be -4 less than x, then less than 1. This one here will just be x is greater than -1 because it goes up to infinity. Or some people say it's -1 less than x, then less than infinity. It's okay even if you say this. Are these things okay here, P? Oh yeah, yeah. Oh, okay. Sorry. Yeah, okay, yeah. Oh, they are saying number, this guy, yeah, it's the same. So if it's like this, you'd have -10 less than x less than or equal to, because it's closed this side, that's a 10. Yeah, this will be, now there's a 4 less than or equal to x less than or equal to 9. This one again, -1, just less than because it's open, then x less than or equal to 5. This one will be x is greater than or equal to 0, or you can write it as 0 less than or equal to x should be less than infinity. Yeah, it's okay. Yeah, so apart from this, the next one now, they want us to show these guys on the number line and also be able to operate the same set operations using them. Yeah, so if we put our expression to be to be shown on the number line, let's say we have what? How can I just say this? A summary is if you have a set, let's say a is equal to -2, and let me use the same example here, at least to kill two birds with one stone. Here they're saying a is what? A is -1 to 6, and it's open at -1 and closed at a is -1, yeah, and closed at 6. Then b is what? B is 0 to 4, open on both sides. Yeah, then C is something that is greater than 4, greater than or equal to 4, so it's closed at 4 up to positive infinity. Then the first thing they want us to get, I'll just do the first one and the last one. They want us to get A minus C, and they want us to get A, or I'll do this one with 3. Yeah, so I'll do the first one and the third one for you to just get the idea. So A minus C. So A minus C is the same as A intersection C complement. So I'll start with C complement first. C is from 4 closed up to positive infinity. This is C. So meaning the complement of C is going to be here, starting from here. If it's closed, meaning C complement will be open, going in the other direction. The red one here is C complement. Is this part okay? So if our C complement, that is things that are outside C, right? Then there's A is negative what? A is negative 1, open, up to 6, closed. So from here up to 6, closed there. That's our A. We're looking for the intersection between these two. The intersection, the part where these two guys are parallel. Yeah, so the answer is just going to be negative 1. The boundary here is open, so follow the boundary is negative open. The boundary here is open as well. So this here will be A minus C, which is A intersection C complement. Is this okay? So it depends with the operation. Is operation says is saying intersection or union? So you mean like if let's say you had A was starting from here. I don't know if this is what you mean, like this. Okay. Then Bafuna, they want intersection, because here now our problem now won't make sense, because if they want the intersection, always go for what's common, right? So here the set would have been an empty set, because there is no part where our C complement is intersecting the A. Okay, so if we take it from here, they want the intersection, right? So if they want the intersection, it simply means that 4 is not going to be included. Intersection meaning still stands. The meaning says what is common between these two guys. And 4 is included in A, in this case. A is in 4 is saying that if they are still asking about the intersection between these two, it means 4, since 4 is included in A but is not included in C, it means it will still be open, because intersection, the meaning still change, the meaning still holds to say we're looking for what's common between A and C complement. So it would have been still open this side. Yeah. Yeah, unless if let's say this one was just like passing, let's say there was a C or starting from somewhere there, then C complement, I mean just passing there, then this would have been closed because it's included. If it up, then again it's closed. So we follow the boundary at that particular number that we are observing. Yes, it will still be included, yes. Yes, it will be included. You are saying if, let's say, it was what? If it was, oh, the same, the actual question. Okay. Oh, union would be, like, union would include it. because union means everything, right? You want me to put it like this? You want me to put it like this, like this, like this? You mean if it was like this? Yeah, so in this case it will be closed. When you're adding, if it's union, when you add closed and open, you get closed. Then when it's intersection, when you add open and closed, we get open. Yeah, even if we were to switch these guys, yeah, even if we were to switch these, even if we were to switch it to be like that, then this to be closed, this is still true, it still holds. What I'm from saying here, yeah, there's the whole thing, the closed plus this would still be the same. Yeah. Yeah. Okay. Yeah, so this should be able to so let's can I do this guy here? Can I do question number the C, this one here? They're saying C, they have given us C complement. Let's just try to do the C minus A, the C minus A, then the answer should be intersect B, so this then intersect B. So this here is the same as C intersection A complement, then intersect B. So we are intersecting all these three sets. Yeah, so we're having what? We're having our AC. So let me just try to open this guy. So our A was from -1 to 6, -1 to 6, closed at 6 and open at 1. That's our A, meaning the complement will be in opposite directions. So would have had closed here and take it to this direction. That's the first piece of A complement. This one will be open, take it in the other direction. So the black one is A complement. A complement is okay how I've sketched it, right? Yeah, then we come to C. C, I'll use blue. So C is from 4 greater than, this is 6 here by the way, so greater than or equal to 4 up to positive infinity. It's closed, going like this. This is your C. Then I'll use purple for B. B is between 0 to 4, so 0 is somewhere there, 0 to 4, and it's open on both ends, open there and also open there. We're looking for the intersection. Where is the black, where are the black lines, the purple and the blue, all intersecting, all parallel to each other? The answer is that there's nowhere, so it's an empty set. This is okay, right? Yeah, so that's what we just do. So this, hopefully, this should be able to help you to answer question number 7 as well, and number 8. So this, it's the same thing again, just check. It's a number line, just follow the same rules again. Yeah, so just try, you try to check if you are able to answer number 8, then you give me feedback, right? Yeah, then look at number 9. Number 9 is on what they're saying. These are rational numbers. So let me explain this a bit here. Rational numbers are numbers that can be put in the form of A over B, and some can end up being in the like, let's say 1 over 2. It can be, let's say 0.5, then 1 over 3. Some of these are continuously going to be having repetitions, so we can just shorten them like this and put a bar. So it's a rational number but just repeating. Now, what they want us to do is to be converting them back to fractions. Do you remember them, or I can just do one example from them? Okay, this is easy. Okay. Okay, so even when there's a negative, right, it's okay? Okay, so when there's a negative, yeah, so we have negative 0.255. The bar is on 55. So we say we let x be equal to negative 0.255 with a bar. It's the same thing, just factorize the negative out. So we say we need to only have the repeating digits alone after the point. Yeah, so we have a 2, which is not under the bar. We have to move it this side. So multiply this by 10. That's going to be 10x is equal to negative 2.55 bar. Then this becomes your equation 1. Then we remove the repeating digit, this on the other side. So we multiply by 100 because there are 2 of them. That's going to be 1000x is equal to negative 255.55. This is second equation. Then now we find the difference between the two. Yeah, so this can cancel, these parts can cancel. So if we were to find the difference here, it's going to be negative 255. It's still the same, minus negative a 2. This side we're having what? There is 1000x minus a 10x. So it's still the same thing. That's going to be a 0. That's a 99. X is equal to negative. That's going to give us a 253. So just do everything in a similar way and add a negative last. That's how we do it if there's a negative. Yeah, so the answer is 2 negative 253 over 990. That's what we get as a fraction. Because I want it in a fraction form, so it just ends here. So the better way to do it is you say x is equal to negative 0.255. So you factorize the negative out. So like solve your question in brackets with a negative weighting outside. So what we're actually solving is 0.255 with this. So solve this the usual way. Then when you're done at the final answer, put back your negative. That's a better way to go about it. No, it doesn't. It doesn't. Yeah, so in an event where they give you something like this, you should expect something that has one part has a band, what one part doesn't have. Like if you have 5.24, for instance, they put a bar there, and they say minus or plus anything. Let's say 7. Let's say 112. So this with a bar, you use the normal thing. You just convert this into the Izankala fraction bar. Then this one here, since there's no bar, you just convert it directly. There's a 1 here, so multiply by the number of steps you need. That's going to be 100 and also 100. So it will be 712 over 100. So whatever you get after you convert this into a fraction, put your answer there minus the 1 over 2 over 100. Then do common denominator and get a single fraction. Yes, this is okay. Yeah. Yeah, so this is what we have. Then the next one, this is under SADS. So like this, they'll always give you a hint, like they're saying, we express this in terms of in the form of p root 3, meaning all the numbers can be reduced by 3. So this is the same as 1 over root what? Is it 4 by 3? Just divide everything by 3. This is going to be root of 16 by 3, then minus 1 over 9 by 3. This here is going to be 1 over root of 4, that's a 2, root 3, plus 1, root of 16, that's a 4, root 3, then minus, this is 3 root 3. Are you okay up to this point here? Yeah, so then from here we just add everything. So this is going to be the same as what? Look at the numbers in front. There's a 2, there's a 4, there's a 3. So we can put what we can say 12, then root 3. So that we can say this root 3 into root 3, it cancels. 2 into 12, that's a 6. 6 by 1, that's a 6. Then 4 there, that's a 3 minus, that's going to give us a 4. So this is the same as that's 9, that's a 5. So we have 5, 12 root 3. Then when you reach at this stage, you rationalize using the down part because you don't want to see the side down. So it's going to be 5 root 3. Then this will be 12 times 3. This will just be 5 root 3, then over 36 down. Is this okay? Yes. So the same applies to the next ones. Yeah, so these guys here, we just reduce them with, so like this 1 over root 5, we just rationalize it rather. This is just root 5 and root 5. This will just be root 5 over 5 down. We just don't want to see the side down. It's okay. Then the same applies with this other guy. It's the same thing. Here's the same thing. Just reduce them. Root 12, that's the same as what? Root 4 times 3. Then you have root 48, that's 16 by 3. This will be root 4, then root 3. Then this will be root 16 and root 3. Root 3 and root 3 can cancel. Root 4, that's what? Root 4, that's a 2. Root 16, that's a 4. This is going to give us 1 over 2. So it's a half. Is this okay? So if it's alone, the conjugate is itself, like the same guy is a conjugate. But if it's attached with something, the conjugate is changing the sign on the middle. Yeah, so if it's 1 over root 11, the conjugate is just root 11. Because even if you add negative, the negative will still cancel. Negative and negative there. Yeah, but if if there are two numbers like this here, the conjugate is going to be very significant because it won't just cancel or go away, because there are two things. We have to expand and expand at the bottom as well. Yeah, so for these ones here, you just expand it first, then before you rationalize. Here, expand the bottom part first. Rationalizing means you have two things, just change the sign on the middle. So same applies with these, all these questions, 12 up to just SADs up to 15. SADs, you know how we multiply, like here, root 11 times 5. You're okay with 5 root 11, right? Root 11 times root 11, that's just as 11. Then 5, negative 5 and 5, that's going to be negative 25. Negative 5 plus this is plus 5 root 11. So this can be added with that. That's going to be 10 root 11 minus, that's a 36. So just leave it there. It's okay. Well, these are okay. You're saying this is just 1 plus root 3, right? even this one. Now saying these ones here, the down part, there's a 2. Yeah, the other ones, there's like a 2. So if you have, let's say, 5 plus root 2, then there's a 2 there. So we say expand the bottom part first. You have 5 plus root 2 and another 5 plus root 2. Solve it first. This will be a 25, 5 root 2. Then last manje, like when you get the this is root that, this is going to be a 27 plus 10 root 2. Once you get this answer now, 27 plus 10 root 2, this is now when you rationalize. Yeah, so this is what you do for this one. It's okay, right? So even up to number 15, the concept is the same. Even these are just two numbers, just rationalize, but you can reduce them first. Like there is a 5 root 75 now minus root 50. We can just reduce them. So this is the same as 25 by 3, right? Then this one here is the same as what? 25 by 2. That's 50. So this will be 5. This is 5 root 3 minus 5 root 2. So you're seeing there's a 5, there's a 5, there's a 5. They can cancel. In short, the question we're actually solving is root 3 minus root 2 down. So rationalize root 3 plus root 2 and also root 3 plus root 2. Is this okay? Yeah, so that's what we do for question 1 up to 15. Then now we talk about this modulus. Modulus, you know what it means? Makes everything positive. So question number, what? Question number, this one is, the answer just going to be 3 over 4. Modulus, if it's positive, leave it the way it is. So this is just 3 over 4. This one here will just be 0.28. This one here will just be 8. This one here, just sum up what you get, write it outside. This will just be a 2 minus a 3. This is a 6 because of the modulus, that's a 6. This is 8 because of the modulus. Put a modulus, that's what? Negative 1. That's negative 2. Put a modulus. The answer is just 1 over 2. Modulus just cancels the negative. If there's any negative, everything becomes positive. That's what modulus does. Is this okay? Yeah, okay, so this is okay. P, let's end here. We'll do the other part tomorrow. We'll do this guy and then tutorial sheet 2. It's not a bad pace, so this is okay. So tomorrow we're going to do proving irrational numbers. There's a question 17 for this tutorial sheet. It's the one for this year, but they just changed question number 17. Like I'm using the old one. This is the last year's one. It's the same with the one you have. So this year there's a different question. If you look at the guy you sent me, or number 17, proving that something is irrational, everything else is the same. So we'll just pick it up from 17 up to 23. The one you have this year ends up to 25. So we'll finish this part tomorrow before we start tutorial sheet 2.